Hello there, and welcome to this collection of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and on this notebook we are going to talk about sampling. So what we are going to do is we are going to take a look at sampling a discrete time signal. Then we're go through some basic concepts in multi-rate signal processing like downsampling, upsampling, reconstruction, and we will finish up with a live spectrogram, a Python example where we can see the effects of downsampling, upsampling, and filtering. So let's get started. To see what happens when we sample a signal, let's start with an analog signal S of t. And then sampling it means to sample the signal at sample intervals capital T or sampling frequency f of s. So let's remember that the sampling frequency f of s is related to the sampling intervals by a relation of 1 over t. So the sampling frequency is equal to 1 divided by the sample intervals. Just for an example, in ISDN systems, it uses 8 kilohertz as sampling frequency. For audio in CDs, so we usually use 44.1 kilohertz. Some other audio systems also use 48 kilohertz. And mathematically, sampling can be formulated as multiplying the analog signal with a Dirac impulse at the sampling time instance n times capital T, where n is the number of our sample. For causal system, n starts at 0, and t is the sample intervals. So here we have a Dirac sequence or a train of Dirac impulses. So they're located at time instance n times capital T. So we have n times capital T, and here's our Dirac sequence. So this sequence or this train of Dirac impulses can be written with this equation here. So this is this delta t here. We will indicate the train of Dirac impulses, and is this summation with the Dirac impulse at time t minus n times capital T. So let's remember that the integral over Dirac impulse is equal to 1. We can see like this here. And the integral over the product of a function with a Dirac impulse is the value of the function at the position of the impulse. So this is a very important property. So the integral over a product of a function with the Dirac impulse is the value of the function at the position of the Dirac impulse. So this is the mathematical formulation of sampling at time point n times capital T. We can now use this description to compute the resulting spectrum with the Fourier transform. First, if we look at the Fourier transform of the analog signal or system, we get this equation here. So there is this integral going from minus infinity to infinity. This is our analog signal or system, and then there is this exponential to the power of minus j omega t, and here the superscript denote the continuous version, and we have this omega, which is equal to 2 pi times frequency, and this omega is the angular frequency. So if we now compute the Fourier transform for the sampled signal, so we are multiplying our signal with the Dirac sequence of the train of Dirac impulses, we can make this replacement. So we substitute this S of t by the sampled version. So it's the S of t times this Dirac sequence. So we replace here, and we will obtain this sum, because only at the sampling time instance the integral is non-zero. We can see from this equation, and we get this sum. And now the superscript d is denoting the discrete version. So we have from here, we went from the continuous version to discrete version. We made the substitution here, and we go from an integral to this sum. And we can see that the frequency variable only appears as omega times n times capital T. And as we said before, t is the inverse of the sampling frequency. So we have this relation here, omega times capital T is equal to omega divided by the sampling frequency, which is defined as this capital omega, and this is what is called the normalized frequency. The normalized frequency is without a physical unit, since the hertz in the omega and in the sampling frequency cancel. And in the normalized frequency, 2 pi represents the sampling frequency, and pi is the so-called the Nyquist frequency. So this is the upper limit of our usable frequency range, and it's defined as half the sampling frequency. Observe that we use the capital omega to signify that this is the normalized frequency. The capitalized version is commonly used to distinguish it from the continuous non-normalized version if both are used. So otherwise, the small omega sometimes is used in the literature for the normalized frequency. If that's all we need, there's no danger of confusion. But we are going to use usually the capital omega for the normalized frequency. To convert the normalized frequency back to the non-normalized one, we simply multiply it with the sampling frequency. So the omega, small omega, is equal to the capital omega, so this is normalized, times the sampling frequency. And to indicate that now we are in the discrete domain, we will rename our signal to x of n. So this was the s of t, now becomes s of n times capital T, and this is our x of n. And then we see that it's the spectrum, or the frequency response is given by this summation here. So this is the frequency response. So here we have the normalized frequency. There is the sum from minus infinity to infinity. This is our signal in the discrete domain, and we have this exponential to the power of minus j capital omega times n. And this equation here we call the discrete time Fourier transform. This is DTFT, because we apply it to the discrete time signals x of n. This can be distinguished from the discrete Fourier transform because the above time signal has infinite length. So we are going from minus infinity to plus infinity. So as n is an integer here, so it's not a real value like t, we have a 2 pi periodicity for the frequent response. So this is a very first important property of discrete time signals, that they have 2 pi periodicity for x, capital X, and capital omega. Here we can see the complex z-plane, and we have here the real and the imaginary axis, and we have values for when omega equals to 0, omega equals to pi, and here is the unit circle where omega is equal to e to the power of minus j omega. And here we can see that in general we obtain a 2 pi periodicity in the frequency domain because of the 2 pi periodicity of the exponential function e to the power j omega. So we also observe that for real valued signal, the spectrum of the negative frequency is the conjugate complex of the positive frequency. This is also a very important property for real valued signals, and here this star denotes the conjugate complex operation, because in our TTFT, so we have e to the power of minus j minus omega n is equal to the complex, the conjugate complex operation. So is the conjugate complex e to the power minus j capital omega n. We also have to use the fact that the conjugate complex of a real value signal does not change it to draw the conjugation out of the Fourier sum. So this also means that for real valued signals, we only need to look at the frequency range between 0 and pi, because the negative frequencies are conjugate symmetric. And because of the 2 pi periodicity, the range between minus pi and pi is also sufficient to look at. This is also again what the Nyquist theorem tells us, that the frequencies between 0 and pi, the Nyquist frequencies, are sufficient to completely describe a real valued signal. So this is a very important property, that for real valued signals, the spectrum of the negative frequency is the conjugate complex of the positive frequencies. And then we have this, what the Nyquist theorem tells us, that the frequencies between 0 and pi are sufficient to completely describe a real valued signal. So far we saw what happens when we sample an analog signal, but now what happens if we further downsample an already discrete signal x of n to reduce its sampling rate. So downsampling by n means that we only keep every nth sample and we discard every sample in between. So observe that this results in a normalized frequency which is a factor of n higher. So this downsampling process can also be seen as first multiplying the signal with a sequence of unit pulses, so it's a 1 at each sample position and zeros in between, and later dropping the zeros. So this multiplication with the unit pulse train can now be used to mathematically analyze downsampling and looking at the resulting spectrum, first including still the zero. So the frequency response now becomes this equation here. So for m, all integers m. So what we can write down downsampling as the multiplication of the signal with a sampling function. So in the continuous time it was this sequence of Dirac impulses, but here is a sequence of unit pulses at position multiples of n. So this is the sequence of unit pulses is equal to 1 if n equals to m times n, or 0 elsewhere. So the sampled signal with the zeros still in it becomes this x of n times this sequence of unit pulses. So we will do the same what we did before, but now we will replace this x of n by x of n times the sequence of unit pulses. And this, so far this is an intermediate signal because it's still there are the zeros there, and the zeros will get removed before transmission or storage to reduce the needed data rate. The decoder upsamples it by reinserting the zeros to obtain the original sampling rate. So observe that this is then also the signal that we obtain after this upsampling in the decoder. So hence the signal looks interesting to us because it appears in the encoder and also in the decoder. So what does its spectrum or frequency response looks like? So we saw that the downsampled signal x of t can be written as the multiplication of the original signal with the unit pulse train delta n. So in the spectrum, on the frequency domain, this becomes a convolution with their Fourier transforms. So first, the Fourier transforms of the unit pulse train is a Dirac impulse train. But this is not easy to derive, so here we will apply a trick to make it mathematically more easy and to get converging sums. This is not something I really enjoy doing. It's a trick that you need. First you have a guess, and then you try to prove that your guess is correct, but you need a lot of experience and intuition to have a good guess. So let's have a guess about what the Fourier transform of the unit pulse train is. So we get Dirac impulses at frequencies of 2 pi divided by capital N times k. So the fundamental frequency is 2 pi divided by capital N, and its harmonics. So the fundamental angular frequency is 2 times pi divided by capital N, because our original sampling frequency was 2 pi, and now we reduced it by a factor of N. So with a constant factor that becomes clear later, we get our gas to this equation here. So this delta 2 pi m n capital omega is guessed to be the Fourier transform of the unit impulse train, so the direct impulse train. So what we need to do, we need to verify it. So the inverse discrete time Fourier transform is given by this equation here. So from here we go to here, and we have that this is the inverse discrete time Fourier transform. So now we have to prove that this is indeed our unit pulse train. So to do that, we will look at this sum, and we see that this is a geometric sum. So it's a sum over a constant with the summation index in the exponent. So let's remember the geometric sum. So if we have the summation, we have an exponential going from k equals to 0 to n minus 1. So what we can do is that we can check what happens when k goes from 1 to n instead from 0 to n minus 1, and then we get this is the s times c. So we have this here. Now if we take s times c minus s, so this is the summation, we'll get that s times c minus s is equal to c to the power of n minus 1, and then if we want to find this s, we will divide this. So s here is like s, and then c minus 1, we put s in evidence, and then we get this thing here. And if we replace the c by this e to the power of j 2 pi n times n, we will get this sum here, and that can be computed in a closed form. So we're replacing c by what we had, and we have this equation here. So in order to get our unit pulse train, this sum must become capital N for n equals to m times n. So how can we check this? We can simply plug this into the sum. So the right part of the sum is undefined in this case, but we get an easy result by looking at the left hand side. So we have that this part here is equal to 1, and this sum becomes n as desired. Yeah? But for n is different than m times n, we need the sum to be 0. So we can now look at the right hand of the equation, and the denominator is not 0, and the numerator becomes 0 when n is different from m times n, and hence we have that this sum is indeed 0 as needed. So this proves that our assumption was right, and we have that the sequence of pulse is given by this equation here. Yeah? And now we can use this expression for the unit pulse train in the time domain, and then we can compute the Fourier transform. So I usually find it quite confusing. We're kind of cheating here, so we're guessing what the Fourier transform of the unit pulse train is, and then we're trying to prove that our guess is correct. So this is our guess. So here this is guessed to be the Fourier transform of the unit pulse. So if this is the Fourier transform, we can take the inverse discrete time Fourier transform. So this is what we're doing here. We're taking the inverse discrete Fourier transform. So this goes here, and this is the formula for the inverse discrete Fourier transform. But this is equal to this, so we put this here, and becomes this thing here. And when we solve this integral, we have this result here. So this is the inverse discrete time Fourier transform. So this is our unit impulse train, and now we need to prove that this is indeed a unit impulse train. So what we do is that we see that this is geometric sum. We use this other mathematic trick to find a closed form for this geometric sum. Here we are replacing c, so c to the power of k. So c in this case is equal to e to the power of j 2 pi capital N times n. So we have that for k equals to, going from the summation from k equals to 0 to n minus 1, and we can simply go from 1 to capital N, and then we have this c multiplying here. Now with this we have that goes from here to here, so we put that this s in evidence. So s is times c minus 1 is equal to c to the power of n minus 1, and then we get that this is the s is equals to c to the power of capital N minus 1 divided by c minus 1. So we use this trick here, and then we replace c by e to the power of j 2 pi divided by capital N times n, and we find this closed form. And now we need to prove that this is a unit pulse train. So this sum must become n for n equals to m times n. So what we do, we replace here n equals to m times capital N, and then we see that this part here is an undefined case, so we have a 0 divided by 0, but on this part here we have that the this here is equal to 1, and then this sum becomes n as desired, and for n different to m times capital N, it needs to be 0, and we can look here. So when we plug this here, and we see that the numerator is unequal to 0, the denominator is unequal to 0, but the numerator becomes 0, and then the sum is indeed 0. Yeah? So we proved that our assumption was right, and we have this equation here for the unit pulse train. So now we can use this expression for the unit pulse train in the time domain, and we can compute the Fourier transform. So we have this here, so we had our signal, and we're multiplying it with the unit pulse train. So the unit pulse train is given by this formula. So we have here that this downsampled version of an already sampled signal. It's like this. Then if we take the discrete time Fourier transform, and then it results in this equation here. So what we're doing is we're taking the dtf, so the discrete time Fourier transform. So this is here, and then there is a summation from minus infinity to infinity, and here we have the e to minus j omega n. So from here we can get this equation here, and this is the result. So we have that the discrete time Fourier transform becomes 1 divided by capital N, and this summation going from k equals to 0 to n minus 1, and then we have this x of minus 2 pi divided by n times k plus omega. So this shows that the sampling still included the zeros leads in the frequency domain to multiple shifted versions of the signal spectrum. So we can also call this multiple shifted version of signal spectrum as aliasing components. So this is a graphical visualization of what indicates here. We have the signal spectrum, and we have the original spectrum, and we have aliasing components. So there are multiple shifted versions of the original signal spectrum. So these aliasing components periodify the spectrum according to the new sampling rate, which is 1 divided of capital N, or 1/nth of the old sampling rate. Hence the new period is 1 divided by n, the old period of 2 pi. So let's observe that the spectral components don't overlap if their bandwidths are below 2 times pi divided by capital N for complex signals, or for real signals it should be below pi divided by n. So this is a very important that the spectral components don't overlap, because if we want to reconstruct the original signal, hence we need to make sure that the aliasing components don't overlap by suitable filtering at the high sampling rate to prepare for the downsampling. Yeah? Let's observe also that the term aliasing in literature is sometimes only used for overlapping aliasing components, but like we do here, we use it more broadly, that we just mean that any additional shifted frequency component, we also call it aliasing. Yeah? So here is an example also including the negative frequencies that now show up above the normalized frequency 1, and in this case 1 is the Nyquist frequency, and we have two sine signals at different strengths at normalized frequencies 0.4 and 0.35. So this can also be seen as a narrowband signal, yeah, for example resulting for a passband filter. So here is our signal, and we have two sine signals with different strengths, and the normalized frequencies are 0.4 and 0.35, and we also see that they show above the normalized frequency of 1, that in this case is the Nyquist frequency. So after sampling, downsampling by a factor of n equals to 4, and still including the zeros, we get the following spectrum. So this is the original signal, and now we are downsampling by a factor of n equals to 4, and we get this thing here. So we can see that we have positive frequencies, we have negative frequencies. These were our original signals, and we have all these spectral copies at frequency shifts of k times 2 pi divided by n from the originals. So we have this aliasing components, so this is spectral copies, so this shifted multiples of the original. So we can see that this original signal in the positive frequency, it appears here, it also appears here, it also appears here, and the original signal, the negative frequencies also appears here, and appears here. So this picture shows that the spectrum still contains the original spectrum plus the spectral copies at frequency shifts of k times 2 times pi divided by capital N. So this is our downsampling factor from the original signal. Yeah? So observe that since we have a real value signal, so the sine waves, the spectrum of the negative and positive frequencies are symmetric around frequency 0. This then leads to the mirrored appearance between the neighboring spectral images or the aliasing components. Okay? Nyquist tells us to sample in such a way that the shifted spectra of our signal do not overlap. Okay? If they overlap, we cannot separate those parts of the spectrum anymore, and we will lose information, and it's not possible to reconstruct. So it's very important that the shifted spectra of our signal do not overlap. So here the conclusion is that sampling a signal by a factor of n, keeping the zeros between the sample points, leads to n-1 aliasing components or spectral copies. Let's see this theory in practice, and we have here an example. So in this example we are using a sampling rate of 44.1 kilohertz, and we will have a sine wave that has a frequency of 400 hertz and 1 second duration. So we need 44,100 samples and 400 periods of our sinusoid in this second. So here we are using Python. I'm importing NumPy. Here I'm defining the sampling rate. Here is the frequency of 400 hertz, and there are two ways we can build the signal. What I'm doing here first is called S, is the sine. So here's 2 pi f, so this is omega. The angular frequency is 2 pi f, and here we have this. This is our time, so it goes from 0 to 1 second in intervals of 1 divided by the sampling frequency. So this is our period, 1 divided by sampling frequency, and we have this sine wave. But we also can define our normalized frequency. So this omega is the angular frequency divided by the sampling rate. So we have the angular frequency is equal to omega is equal to 2 pi f. So this is what we're doing here, and we are dividing by the sampling frequency, and now we're having the sine of the normalized frequency, and here we have our time in terms of samples. So it goes from 0 to 44,100 samples. That means it's 1 second, and in steps of 1, so it's n is equal to 0, 1, 2, 3, and so forth. And here we can hear our signal. So this is 1 second. This is our sine wave at the sampling rate of 44.1 kilohertz, and this is 400 hertz sine wave frequency. So if we plot the first 1000 samples, so here I'm plotting the both signals just to prove that they are in fact the same. So we have our sinusoid, the first 1000 samples. Now what we can do, we can multiply this sine tone signal with a unit pulse strain. In this case we are going to use a factor of n equals to 8. So here we are generating the unit pulse strain. So first I'm defining an array full of zeros, and then I'm inserting a 1 into every n equals to 8. So the multiples of 8. So what we have here is this unit pulse strain with zeros in between them. So there's just this our array of zeros, and I'm inserting a 1. So here what we have, a 1, then zeros, then another 1, zeros, and then we can listen to this unit pulse strain. So this is how it sounds like, and we are now multiplying our signal with the unit pulse strain. So this is what I'm calling here SDU, so our signal times this unit pulse strain, and this multiplication is also called the frequency mixing, and we can plot the result for the first 100 samples. So this is our our original signal in blue, and we had sine wave. Now we're multiplying this signal with this unit impulse train. So we have multiplying with this, and what we have is this downsampled, still with the zeros on. So when we multiply, we get this in red, and we have here, this is the downsampled version with the zeros on. So this is our signal, still with the zeros in it, and we can take a look at the magnitude spectrum in dB. So here we have the magnitude spectrum of the original signal, and we have this magnitude here. So this is the normalized frequency, and this is the magnitude in dB. So this is what we're doing here. We're using frac Z to have this frequency response of our signal. So this plot shows the magnitude of the frequency spectrum of our signal, and we can observe that this is normalized frequency. So in this case, the Nyquist frequency is equal to pi, so it's 3 goes until 3.14, and it means that in this case is 22,050 Hertz, so it's half of the sampling frequency. So our sinusoid should appear as a peak at the normalized frequency of 400 Hertz divided by 22,000 times pi, and we have this value here, 0.05, and indeed if we look here, we have approximately here 0.05. And now we can compare this to our signal with the zero, so it's the SDU, and we are plotting here now is the normalized frequency and the magnitude frequency response of the original sinusoid and the sinusoid with zeros. So in blue we have the original, so it's the same as this one here, but now we have this downsampled version with the zeros on, and we have this one in orange. So it's very interesting to note that now we see that we have as our 400 Hertz tone, but also we have 7 new aliasing components. We have 1, 2, 3, 4, 5, 6, 7. So we go from the blue to the orange, and observe that always two aliasing components are close together, and this is because that the original 400 tones also has a spectral peak in negative frequency at minus 400, so it's a normalized frequency of minus 0.05, and this is why they are appearing here together, because here we would have in the negative frequencies also a peak. This is a characteristic of the sinusoid, and we see now we can also listen to the signal still with zeros. So we hear that it's quite different from our original signal because we have, oh no, this is the unit pulse. This is our original signal. So this is our original 400 Hertz. We multiply with this unit impulse train, and what we get still with the zeros on is the downsampling version, and we have this 400 tone and 7 new aliasing components. We have now another example, and this is a real-time Python example, and here you can hear that it sounds quite different from the original because of strong aliasing components. So this example takes the microphone input, it will sample it without removing the zero, and it will play it back in real time. So we'll construct this unit pulse train using the modulus function. So this is how we are constructing here a unit pulse train with a 1 at every nth sample. So this was originally an example from Professor Schuler, which I updated, made some improvements, and ported to run inside Jupyter notebooks. So now we have a small GUI. So let's go through the code. So I'm importing these libraries. We are going to use PyAudio to handle the audio. Then we are going to use NumPy. We are going to use IPy-widgets to have some GUI, the graphical user interface with some buttons and checkbot. And we are going to use threading to run the audio part inside the thread and still be able to interact with the graphical user interface. So when I run the cell, it will automatically start this PyAudio streaming. So I don't need a start button, but I'm doing here is a stop button. So when I press this stop button, I want to stop. So the stream is going to stop, and I will close. I will terminate the PyAudio instance, and I just print that the PyAudio is terminated. So here I am defining a sampling on that is going to be true or false. So this will control when we press this sampling checkbox, and then we'll turn on sampling with this downsampling with zeros. And so this is the defining the stop button. Here is the function that is called when the stop button is pressed, and I'm just playing the stop button. And here is this checkbox to turn on, to turn sampling on and off. And this is the function then it's called when there is some interaction with this checkbox. So here I'm defining that n is equal to 8. This is the downsampling factor. Here I'm creating the unit pulse train using this modulus function here. So there's a 1 in every nth sample. This is what we are doing here. Here I am using the PyAudio now in callback mode. So if you've been following our tutorials, you've seen we've been using PyAudio in the blocking mode. So we have this string read, but in this case there will be this callback will be called all the time that we have samples, and then we can do some changes with this data, and then also to playback. So this is here we're creating an instance of PyAudio. Here we are creating the string, so we are using 16-bit integers. This is one channel, so it's mono. Here's the sampling rate we are using, output true and input true, so it means that we are using the microphone input and the speaker's output. We are using 1024 frames per buffer, and then we have this the callback function that this is. So every time we have enough samples, and then this callback will be called, it will execute. And there's recommended by PyAudio to have this keep alive function here. So we use the while this stream is active, it just sleeps. And I'm just including here this stop. So when we press stop, also interrupts this infinite loop here. Finally, I'm using a thread to run this keep alive, because as we have an infinite loop here, and I don't want it to block, and we're not able to interact with the graphical user interface. So this part runs in a separate thread, and the PyAudio, when we are using also the callback mode, is using another thread. So here I'm starting the stream. Actually, I don't really need to use this, because by default, if you don't put that the start stream is false, when you create the stream by using this PyAudio open, it will already start. So this is not necessary. And then I'm starting the thread to have this keep alive. So let's execute the cell. Aliasing, A test, check 1, rock and roll, heavy metal, jazz and blues. So now we are going to turn on the downsampling with zeros by a factor n equals to 8. And now we have the downsampling version with the zeros on. Rock and roll, hey, check, blues, jazz, funk, soul, rock and roll. And now back without the downsampling. So we can see the aliasing components. And if we stopped, the pi order is terminated. And this was our real-time example, just to take a look what happens with downsampling without removing the zeros. The final step of downsampling is now to omit the zeros between the samples to obtain the lower sampling rate. So we will call the signal without the zeros as y of m, where the time index m denotes the lower sampling rate as opposed to n, which denotes the higher sampling rate. So when we go back to our Python example of the sinusoid seen before, what we're going to do now is to remove the zeros. So this is what we're doing here using this array indexing. So we're just taking the n equals to 8 multiples of this signal. So we're removing the zeros, we're just keeping the non-zero values, and then we're plotting here. So this is what we have. This is the downsample without the zeros, and we see that before we were plotting 100 samples, but now when we remove the zeros we are left with 12 samples from n equals to 0 until n equals to 11. And if we take a look at the spectrum without, this is the spectrum without the zeros. So we remove the zeros, we're calling ST, is with the zeros removed, and we have this spectrum here. So there's the magnitude in dB and the normalized frequency, and we see here that now the signal appears at a normalized frequency of 0.455, and this is a factor of 8 higher than before when we had the zeros in it, because now we reduce the sampling rate by 8. And how can we explain this? We can explain this because now we have a new Nyquist frequency, which is the 22,050 divided by 8, and our normalized frequency becomes the 400 Hertz we had times pi divided by the Nyquist frequency times 8, and this is 0.455. That means that removing the zero scales or stretches our frequency axis. And as I said before, in our time domain plot we only have 12 samples left, because when we plotted the 100 samples, but now we remove the zeros and we get 12 samples. So this is what's shown here, and this is what's showing here with the new normalized frequency, because we changed the sampling rate by 8. By changing the sampling rate by 8, we also have a new Nyquist frequency, and then we need to this means that removing the zeros scales or stretches our frequency axis, and we need to adapt to calculate the normalized frequency. So how are the frequency response of the spectra of y of m and xt of n are connected? So what we can do, we can simply take the Fourier transforms of them. So this was the signal still with zeros in it, so most of the sum here will only contain zeros. So what we do, we only need to let the sum run over the non-zero entries, so it's only on every nth entry. So we replace n by m times n, and we will have from here to here we're replacing n by n times n for all integer n. So now is without the zeros, and we can make the connection to the Fourier transform of y of n by making the index substitution m for n in the sum. So we have this thing here, and this is this result, and it shows that the downsampled version with the removal of the zeros has the same frequency response, but the frequency variable omega is scaled by the factor of n, capital N, which is the downsampling factor. So we can see the difference. Here was the Fourier transform of the signal with the zeros. Here's the Fourier transform, the signals without the zeros, and we get this factor n that is scaling the capital omega. So for instance, the normalized frequency pi divided by capital N before downsampling becomes pi after removing the zeros. And it shows that a small part of the spectrum before downsampling becomes the full usable spectrum after downsampling. So observe that we don't lose any frequency in this way, because we had multiple copies of the spectrum in steps of 2 pi divided by n, and the spectrum already has a periodicity of 2 pi divided by capital N. So this means that the spectrum between minus pi divided by n and pi divided by n, for instance, but we could take any period of length 2 pi divided by capital N, contains a unique and full part of the spectrum, because the rest is just the periodic continuation. And we can see in these pictures here. So this is the magnitude spectrum of a signal. These two boxes are symbolizing a passband or of an ideal filter. In this case, it's a high pass. So this is our signal, and we are doing this high pass. So this is what it does after passing through a high pass. And then there's the signal spectrum after the multiplication with the unit pulse train, when you're using n equals to 2. So we are setting every second value to 0, and still the 0 are still in the sequence, and we have a shift and add the signal by multiples of 2 pi divided by 2, which is equal to pi, and in effect we obtain mirrored images of the high frequencies to the low frequencies. So we are assuming we have a real value signal. So observe that the mirrored spectra and the original spectrum, they don't overlap, and it makes the reconstruction easy. So this is the signal spectrum after downsampling, removing the zeros by n. In this example, n is equal to 2, and can observe the stretching of the spectrum by a factor of 2. So in conclusion, we've seen here that the removing the zeros and downsampling and removing the zeros, it scales or stretches our frequency axis. We've seen a downsampling, and now it's time to take a look at upsampling. That this is still what's missing in our system. So upsampling is the opposite operation of downsampling, and it's the case where we would like to increase our sampling rate. Yeah? So what we want to do is we want to upsampling by first inserting n minus 1 zeros after each sample, and then we have some interpolation filter for it. Yeah? It can be a high pass or a band pass or a low pass, so it depends the frequencies we want to fish out, yeah, from the downsampled version. So what we do is we take the signal at the lower sampling rate. So this was the y of m. Yeah, the index m is indicating the lower sampling rate, and then the signal at the higher sampling rate with zeros in it was the x of t superscript d of n. So index n indicating the higher sampling rate. So we can see that this is the reverse operation of the final step of removing the zeros for the downsampling. So we can take our result for downsampling. So we had this thing here, and we can see that it becomes, we're not just coming from y of m, going to the now upsampled signal x of t of n. So for instance, if we had the frequency pi before upsampling, then it becomes pi divided by 2 for the upsampled signal, in case we have a upsampling factor of n equals to 2. So in this way we now get an extended frequency range. So since now we have again the signal including the zeros, we again have this periodic spectrum as before, and as we progress through the same steps backwards now. So we can also see that the result of upsampling is periodic in frequency, because the signal was 2 pi periodic before upsampling anyway, and after upsampling the frequency scale replaces 2 pi times capital N by 2 pi. We've seen downsampling, we've seen upsampling, and we can see the reconstruction. So in the case that the aliasing components don't overlap, we can perfectly reconstruct the signal by using a suitable filter. Yeah? So we can make sure that they don't overlap by filtering the signal at the higher sampling rate before they can overlap, as we did in our high-pass example. Yeah? If they already overlap at the lower sampling frequency, it will be too late to separate the different components, and the signal will be already destroyed. Yeah? We can perfectly reconstruct the high-pass signal in our example if we use ideal filters, yeah, using upsampling and the ideal high-pass filtering. So in this way, we have for analysis and synthesis the following picture. So here we had a high pass, and we had downsampling. Here how the spectrum looks like after high pass, after downsampling, and then for synthesis we have upsampling, and then we have high pass filter, and we get this and this. So it's very interesting to observe that we violate the conventional Nyquist criterion, because our high pass passes the high frequencies, yeah? But then the sampling mirrors those frequencies to the lower range, such that we can apply the traditional Nyquist sampling theorem. So this method is known as the band-pass Nyquist. Yeah? The band-pass Nyquist is an important principle for filter banks and wavelets. Yeah? The band-pass Nyquist says that we can perfectly reconstruct a band-pass signal in a filter bank if we sample with twice the rate as the bandwidth of our bandpass signal, assuming we have ideal filters to avoid spectral overlap of the aliasing components. Yeah. In general, this is true for complex filters. For real-valued filters, we need to observe that this simple assumption only works if we have bandpass filters which start at frequencies pi divided by capital N times k, an integer k. So otherwise we could have overlap to the alias components. Okay? So let's take a look at an example. So we have a real valued bandpass filter which starts its passband at epsilon and ends at epsilon plus pi divided by capital N. So since it's real values, the passband also appears at the same negative frequency, so we always need to consider the negative frequency. And after multiplication with the unit pulse train, we get out with one aliasing component out of N by shifting the negative passband by 2 pi divided by capital N to the positive frequency, which results in the range from pi divided by capital N minus epsilon to pi divided by capital N. 2 pi divided by capital N minus epsilon. So here we have an overlap from pi divided to capital N minus epsilon to pi divided capital N plus epsilon, and we could not perfectly reconstruct our signal. Yeah? So sampling of twice the bandwidth for real valued signals and filters only works if the bandwidths are aligned with pi divided by capital N times k. Yeah? And what could we do otherwise to avoid overlapping aliasing components? We can simply increase the sampling rate, for instance, to twice the usual sampling rate, so 4 times the bandwidth, to have a safety margin. Yeah. Another possibility would be to shift the bandpass signals in frequency such that they are now aligned with the mentioned grid. So this is an important thing to have in mind, that for real valued signals, yeah, this bandpass Nyquist theorem indicates that we must have bandpass filters which starts at frequency pi divided by capital N times k. So otherwise we could have overlap the alias components. And to solve this problem, or we can use a higher sampling rate, so 4 times, for example, the bandwidth, so having the safety margin, or we can also shift the bandpass signals frequency that in a way that they are aligned with this grid of pi divided by capital N times k. So observe that this restriction is not needed for complex signals or filter banks. This is also why complex filter banks are used for example, in acoustic echo cancellation, because there the sampling rate can be increased by a certain fraction, less than a factor of 2, to reduce aliasing artifacts and still have lower complexity. Summarizing, if our band borders are aligned with multiples of pi divided by capital N, then we can downsample by n. Otherwise, we are on the safe side by using n divided by 2 as downsampling rate for real valued signals. For complex signals, we can always downsample by n regardless of the exact placement of the bandpass filter. So here we're just comparing with the standard Nyquist case. We have a low pass signal which we downsample and reconstruct. This is the last part of this notebook, and what we're going to do is to have a Python example. So this is a live spectrogram. Stay here. So we have sampling, and downsampling, upsampling, and the effects of low pass filtering. So let's go through this code. So this is some Python imports and some configurations. So we're going to use PyAudio again to handle the audio streams, and we're going to use NumPy for Python arrays and some mathematical operations. We're going to use SciPy signal for implementing a filter. We are going to use matplotlib to plot, and we're going to use IPyWidgets for a graphical user interface. Again, we will have a separate thread. In this case, we're going to use the blocking mode of PyAudio. We'll run it into a separate thread, and then we can also interact with the graphical user interface. Here are the parameters. We're going to use the block size 2048 samples. It's mono, so channel equals to 1. This time we're going to use a sampling rate of 32 kilohertz. The downsampling and upsampling rate is a factor of n equals to 8. We are going to use 16-bit integers. We are going to use here for the spectrogram number of FFT points of 1024, and the overlap value for the spectrogram is 512. So here, let's run this the cells. Here we are defining our low-pass filter. So this is an II, infinite impulse response filter. We are using here the more normalized frequency, so it's 1.9. So it's as the factor is 8. So we are using filter with the cutoff frequency of 2, approximately 2, divided by the Nyquist. So this is what we have here, and I'm just putting 100 Hertz for margin. This is the ripple 60 dB, and we're having a low pass filter. And here are the memory for the filter, and this is just a Boolean variable to turn the filter on and off that we are going to use inside our function and to control with the graphical user interface. We can also control the sampling, or it's this downsampling followed by upsampling to turn on and off. Here we are using just some control for plotting. So it's Pi audio and Python in general not very good to handle real-time audio, especially if you want to process, filter, and also to plot at the same time. So this this control here is just to not to plot every time, but to have a certain number of to choose a certain frame rate for plotting. Here we're defining this function called the run spectrogram that will be run inside the thread. So this run spectrogram, we are reading the data stream from Pi audio. This is what we are doing here. Then we are converting this stream into usable data, and we are converting to floats. Here, this is our filter. This is the low pass filter before downsampling. So this is downsampling followed by upsampling. So this is what we are doing here. We are using again the multiplying with the post train using this modulus function, and here is the low pass filtering after upsampling. So this is the combination of downsampling and upsampling, and here we are playing back the filtered and sample version of our signal, and here we are updating the plot. We are calculating a spectrogram, and here we are setting the new values for the initial plot. At this point here we are creating a graphical user interface. So we have a button to start, a button to stop, then a checkbox to turn downsampling and upsampling on and off, and a checkbox to turn the low pass filters both before downsampling and upsampling on and off. So these are the functions that are called when there's an interaction with this button. So this is the start button, will start the thread, and the thread, this function here will run inside this thread. This is to stop. When you stop, we're going to close, to stop the stream, to close, to terminate the Pi audio instance, and also to close the plot. Here we're turning the sampling, downsampling and upsampling on and off. Here we are turning the filters on and off, and here we are creating some boxes to hold the buttons. Here we are defining the thread, and the run spectrogram function will run inside this thread, and also will pass the toggle run as an argument for this function that we want to stop this. There's this infinite loop here. We want to interact with our graphical user interface, and when we press stop, we want to break this loop and stop. Finally, we are creating our Pi audio instance. We are creating and opening our stream, and then we will read the stream and run our example. This is the last part of the code where we'll initialize the plot with some initial values and display the graphical user interface elements. So we're displaying the box we defined before. We're creating here our plot, setting with some initial values, and we also have a close event for when we close this graph, and then it will terminate the stream, terminate by audio. So rock and roll, tests, blues, jazz, and funk. Keep up the funk. The rock and roll, yeah. So we have our spectrogram. Now we will turn on downsampling and upsampling. So at this point, there is no low-pass filtering, and we can see the aliasing components when we have the downsampling and upsampling without the filters. Hello, A. But now we turn on the filters. A. Hello. Teste, teste. Som. 1, 2. Teste. A. Teste. A. Som. Rock and roll. Rock and roll. Rock and roll. A. Rock and roll. Rock and roll. Som. So we see here that we can reconstruct here at this point. We just reconstruct 1/10 of the spectrum, and we would need more filters to reconstruct the full range of frequencies of the signal. Here we just have one low pass, but if we have here a downsampling upsampling rate n equals to 8, we can use 8 different filters, and then we fish out from the aliasing components the frequencies we want, and we end up with all the frequency range, and we can reconstruct the original signal if we have more filters. In this case, we just have a low pass filters, so we just seen here that we are removing some aliasing components, and we just have here the reconstruction of 1/10 of the original signal. So that's it for this notebook, and see you on the next one.